Now let's see 2011 past paper. And now we are going to solve this 2011 past paper using the Hungarian method. The first step is we have to do the row reduction. To do the row reduction, we have to identify the smallest value in each row. So here in the first row it is 8, in the second row it is 9, in the third row it is 10, whereas in the fourth row it's 10. So from each smallest value in that particular row, we have to deduct all the other values. So you can see in this table, I have deduct all the values from the smallest value in that particular row. So you will get a row reduction table like this after deducting the smallest value in each row. Now the next one is we have to do the column reduction. So in the column reduction, we are going to identify the smallest value for each column. So in the first column, it is 0, and in the second column, it is 1. In the third column, it is 0, whereas in the fourth column, it is also 0. So then when we are deducting the smallest value from each column, you will get the column reduction table as follows. So from the column reduction table, we have to test the optimality. So what we are going to see is we have to see whether we will be able to cut the zeros with minimum straight lines. So here I have used 3 straight lines to cut the zeros. So you can see the number of lines are not equal to the number of rows. Therefore, this is not the optimum solution. To arrive at the additional zeros, what we are going to do is we are going to identify the lowest value of the remaining elements. So from the remaining elements, I am going to identify the lowest value, which is 2. This is also known as the theta value. So I'm going to add this theta value to the intercepting points. Here there are 2 intercepting points, 10 and 8. So I'm going to add that value to these intercepting points. Then from the remaining elements, I'm going to deduct the theta value. So you can see in the next table, I have added 2 for the intercepting points and I have deducted 2 from the remaining elements. And I have written the same value for the elements which have cut with the straight lines. In the next stage, what we are going to do is we are going to test the optimality. For that one, we have to see whether we will be able to cover each zero with minimum number of straight lines. So here, I am using 4 straight lines. Since the number of straight lines equal to the number of rows, so this is my optimum solution. Now let's see the possible alternatives. So first one, we have to see whether are there any single alternatives. So here for machine 1, we just have one single option, which means we have to allocate machine 1 for J4. Other than that, there is no other alternative. So first we are going to allocate machine 1 for J4. Then we go for machine 2. When it comes to machine 2, there are 2 available options. First, we can allocate machine 2 for J1, or If not, we can allocate machine 2 for J3. So if we select machine 2 for J1, we won't be able to allocate it for J3. So, since machine 2 has been allocated to J1, there's no need to allocate machine number 3 for the same job. Therefore, we are going to ignore that option. So, now what we have, we can allocate this machine 3 for J2. Since we have allocated machine 3 for J2, there's no need to allocate any other machine. So, we are going to ignore the option of M4. Then, for M4, we just have a single option of allocating it to either J3 or ignore it. So, since this is the optimum solution, and at the same time, since this is the only chance to allocate a machine for J3, we are going to proceed the option of allocating M4. So now you can see for each machine we have a unique job. Now based on the original matrix, we have to identify the cost for each alternative. So you can see that when we allocate J4 for M1, the cost is 10, J1 for M2, the cost is 9, J2 to M3, the cost is 11, and J3 to M4, the cost is 10. So the overall cost is resulting 40. Since there are more allocations for M2, M3 and M4, rather than stopping at a single solution, what we have to do is we have to see whether there are any other options which will result in lowest cost. Now let's go for allocation 2. So as I explained earlier, since there is single allocation for machine 1, we have to go for it. Therefore, for job 4, we are going to allocate machine 1. Then, in the earlier one, we have got machine 2 for job 1. So now, in this allocation, we are going to other way around, which means we are going to allocate machine 2 for J3. Then, if we allocated machine 2 for J3, we won't be able to allocate machine 2 for job 1. Since there is no allocation for J1, we are going to allocate machine number 3 for J1. So when we are going to allocate machine number 3 for J1, we won't be able to allocate machine number 3 for J2. Since there is no other choice for machine number 4, we have to go for J2 or the job 2. So if we allocate machine number 4 for job 2, we can't allocate machine number 4 for job 3. Why? Because we have already allocated machine number 2 for job 3. Since there is no other choice for machine number 4, we have to go for J2 or the job 2. So if we allocate machine number 4 for job 2, we can't allocate machine number 4 for job 3. Why? Because we have already allocated machine number 2 for job 3. After doing the allocation, now we have to go back to the original table and identify the cost behind each allocation. So when it comes to J4M1, the cost is 10, and J3M2, it is 13. For J1M3, it is 8, and finally for J2 M4 it is 9. So you can see that the overall cost is same as earlier. In the interpretation, you can conclude that the company can go for either allocation 1, which is J4 for M1, J1 to M2, J2 to M3, J3 to M4, or allocation 2, which is J4 to M1, J3 to M2, J1 to M3, J2 to M4 to minimize its assignment problem.